9.2 Air Standard Otto Cycle. The Air Standard Otto Cycle is an ideal cycle to model spark ignition internal combustion engines. We use Air Standard analysis for the Otto cycle. The Otto cycle takes place in a closed system. The mass of air is fixed throughout the cycle. The cycle consists of 4 internally reversible processes. So let's see the processes on a TS and PV diagrams. We can see 2 isentropic processes and 2 constant volume heat transfer processes. On the x-axis, A is the top dead center or TDC. B is the bottom dead center or BDC. From 0 to A, this is the clearance volume. Let's take a look at each process. Process 1-2. The piston starts at state 1. The piston is moving from BDC to TDC. It is an isentropic compression. The isentropic is an adiabatic and reversible process. In other words, there is no heat transfer across the system and no irreversibilities are present during the process. It is represented as a vertical line on a TS diagram. No entropy change. But the pressure increases and the volume decreases. Some work is done on the system. All it consumed work. Energy balance equations for a closed system can be written. So we are neglecting the changes in kinetic energy and potential energies of the system. For convenience, we assume all works and heat transfers in the cycle analysis are positive quantities. So I've added negative sign here. As we know, work is done on the system. We know that there is no heat transfer during the process. It is an isentropic process. Also from the TS diagram, the area under the process line represents the heat transfer. For a vertical line on TS diagram, no heat transfer. So the energy balance is reduced. The work done on air in the system is the specific energy difference between state 2 and 1. Process 2-3. At state 2, combustion takes place, so there is a sudden jump in the pressure. The piston is not moving. It stays at TDC during the process. The volume of the air remains constant during the process. That suggests no boundary work during the process. See the vertical line on the PV diagram. The volume remains constant. We have temperature and pressure increases during this process. The combustion process is replaced by the heat addition to air from an external source. Using the energy balance, we got the heat transfer to air is the specific energy difference between state 3 and 2. Process 3-4 is a power stroke. The piston is moving from TDC to BDC. It is an isentropic expansion. The entropy remains constant. Again, there is no heat transfer during the process. Pressure and temperature decrease. Work is done by air. Using the energy balance, we got the work done by air is the specific energy difference between state 3 and 4. The final process 4-1 is a constant volume heat rejection. The piston stays at BDC. The volume of air remains constant, no boundary work. Pressure and temperature decrease. Heat is rejected from the air. So what we have, Q for 1. The heat transfer from air is the specific energy difference between state 4 and 1. This completes the cycle.